Alright, good afternoon everyone. Welcome to our today's chemistry lesson on chemistry. Now, looking at spectroscopy today. Spectroscopy is the interaction of light with matter. Now, it's actually a technique used to study matter with light. So, if I'm to detect the composition of an organic compound, such as compounds found in leaves or various organic sources, I want to determine their structure, their elemental composition. A technique I can employ is spectroscopy. Now, spectroscopy makes use of an instrument called a spectrometer. Now, the word spectrometer is different from a spectrophotometer, but we make use of a spectrometer and spectroscopy. Now, spectroscopy, in a spectrometer, we have various components. And the various components of the spectrometer is the light source, the monochromator, the cuvée, and the detector. Now, these are the basic components. Various spectrometers have their various components. Some added prism and scope, so they can have some other things, but these are the basic components of every spectrometer. Now, remember, the goal is to determine the structure, composition, or the form of the organic compound with light. Now, so the light we can come and encounter in spectroscopy, the various forms of light are the gasula, now which stands for gamma ray, X-ray, UV ray, visible light, infrared spectroscopy, then radio wave or microwave. Now, these lights are arranged in order of their increasing wavelength. Now, but however, it should be noted that not all of them are being used in spectroscopy, because some of these rays, some of them are usually very dangerous or have extremely low wavelength. Like the gamma ray, we cannot have gamma ray spectroscopy, because the wavelength of gamma ray is very, very minute, so small, that's very high frequency. So wavelength is inverse of frequency, all of that are in physics. Now, for a spectrometer, we have light source, monochromator, cuvée, and the detector. Now, the light source usually produces light of various radiations. So I can have a light source producing gamma ray, X-ray, UV, light, infrared. Now that's the light source. So this is the light source. Produces light of various wavelengths, various types of light. Now, it is the role of a monochromator to make the light one type of light. So I can have light of various sources. Then the monochromator will make it one particular type of light. So I can have all this spectrum of light coming in, but the monochromator will put it into one type of light. So maybe I have to perform IR spectroscopy, infrared wave spectroscopy. Now, what the monochromator does, it filters all other forms of light, leaving only the infrared ray to pass through. Now, the next main part is the cuvée. Now, the cuvée means the sample holder. Yes, the sample holder is made up of different materials. The cuvée can be made up of different materials, depending on the spectroscopy technique to carry out. Then finally, we have the detector. The detector is the result. Detect the result of the. That way I can get my results, and the results are usually in peaks, depending on the spectroscopy technique we are carrying out. Now, quickly, let's look at the various techniques and let's see some of the various types. Now, first of all, I'll look at the various and the common types of spectroscopy. So, the common type of spectroscopy are 4 types. Very common 4 types, actually 5, actually. But the last one is not a true spectroscopy technique. So, the first one is RO spectroscopy, visible spectroscopy, UV spectroscopy, NMRO, and mass spectroscopy. Now, first of all, the mass spectroscopy is not a true spectroscopy technique because it does not use a radiation, it does not use a light ray. It uses a fast-moving electron, yes, to split the molecules and get the various masses of the element present. So the mass spectroscopy is not a true form of spectroscopy. So the true form of spectroscopy is the IRO, visible, UV spectroscopy, and NMRO spectroscopy. Now, quickly, for the IRO spectroscopy, let me start with UV. For UV spectroscopy, the wavelength of the light is between 400 nanometers to about 800 nanometers. 400 nanometers to about 800 nanometers for UV spectroscopy. While for visible spectroscopy, is around 185 nanometers to 400 nanometers. For IRO spectroscopy is around 700 nanometers to 500,000 nanometers, which is 500 micrometers. So for NMR spectroscopy is usually above. So for the rate to be NMR, now NMR is kind of complex because NMR make use of radio wave or microwave for NMR in the presence of a magnet. So NMR stands for nuclear magnetic resonance. So the atoms are going to resonate, the nucleus of the atoms are going to resonate in the presence of radio wave and a magnet. So that's the meaning of NMR. Our spectroscopy 2 video will be looking at NMR spectroscopy in details in our next spectroscopy video. But for this one, we'll look at the basic concepts concerning IRO, visible, and UV spectroscopy. Now, quickly for IRO spectroscopy, the common source that can produce the IRO light, infrared ray light, is the nest glower. Now, the nest glower is actually an instrument made up of a transition metal oxide, such as zirconium oxide, or I can use what's it called? I can use this cadmium oxide. Now I'm going to heat it to about 1,500 degrees Celsius, and I'm going to get various form of light in 100 degrees Celsius, and I'm going to get various form of light in which the IRO light is more. So the nest glower is a typical example of an instrument used to produce infrared spectroscopy. So the light source usually in nest glower here for IRO spectroscopy. Then I have a monochromator that will separate every other light, leaving only IRO light to pass through. Now for IRO spectroscopy, the cuvee should be made up of rock salt. So for IRO spectroscopy, my cuvee should be made up of rock salt. When I mean rock salt, I mean the material should be made of something like NaCl. So the cuvee should be made up of a material like NaCl or KCl, rock salt, for IRO spectroscopy. And IRO spectroscopy should be noted is to determine the presence of functional groups, the presence of atoms. Some atoms are IRO active, others are IRO inactive. So example of IRO active molecules, let me just jump to that. IRO active molecules are molecules with dipole moment. They have dipole moment, the charges can be separated on them. E.g., I have HCl. Yes, HCl is an IRO active molecule. So this is an example of the IRO active molecule, HCl, H2O, because I can separate this compound into H plus, Cl minus, H plus. IRO active molecules are molecules that have dipole moment. I already said that. They are molecules that are polar, first of all, and they usually have an uneven separation of charge. For instance, an IRO active molecule such as HCl, now you see something like this, you see the separation on H plus Cn minus. So these molecules with dipole moments that are polar are IRO active. So these IRO active molecules can be, their presence in an organic compound can be tested for by the IRO spectroscopy. IRO spectroscopy is used to determine the type of bond present in an organic compound, the type of bond, the functional group. Don't forget that the cuvee is made up of rock salts such as NaCl, KCl. Yes, we don't use glass or quartz because glass or quartz can absorb IRO light, and the IRO's radiation, the wavelength is around 700 nanometers to about 500 micrometers, which is 500,000 nanometers. So for other spectroscopy, like the UV spectroscopy, now the UV spectroscopy and the visible spectroscopy often work together. We call them UVVs in the industrial world. They are called UVVs. They used to analyze compounds that have double bonds. Usually, they used to determine the presence of double bonds in a compound. To be very specific, they are used to determine conjugation. What's a conjugated double bond? Now, conjugated double bonds are double bonds that have the double bonds or two double bonds in an organic compound, in which the double bonds are separated by a single bond. So to determine conjugation in organic compound, we can use the UVV spectroscopy. So let me analyze visible spectroscopy and UV spectroscopy differently. Now for a UV spectroscopy, the light source will usually be one that can produce UV light, such as an hydrogen discharge tube. It's a very good UV ray source. Then the argon lamp, also we can use the deuterium lamp also, so to produce the ultraviolet radiation. So ultraviolet radiations, this hydrogen discharge should can produce mainly ultraviolet radiation. The other radiations, such as the visible light, but the monochromated will make it to one light, one particular light. Then when this light passes through the cuvee, the light is being absorbed by the material. So we have some materials here, usually double bond material with double bond, presence of double bond, usually presence of conjugation. Now, these materials will absorb this UV light, and not all the light will be absorbed. Some of the light will be transmitted. So the light that is transmitted is read by the detector and used to interpret this compound. Now, we should also note that the cuvee in UV spectroscopy is made up of quartz. The cuvee is made up of quartz. We don't use glass for UV because glass can absorb ultraviolet radiation. So it's made up of quartz. So when the light passes through the cuvee, quartz will not be able to absorb the UV. So just the material that absorbs the UV, and some of the materials are going to, some of the light will be transmitted and be read by the detector. So that's simple for UV. Like I said, UV spectroscopy and visible spectroscopy work hand in hand. It's term UV. Like I said, UV spectroscopy and visible spectroscopy work hand in hand. It's term UVV. So usually the spectrometer is called the UVV spectrometer. So, and UV is to determine the presence of double bond. So for visible spectroscopy, on the other hand, the main difference is that the visible spectroscopy will use a visible light which have wavelength of 185 to 400 nanometer. UV light have wavelength of 400 nanometers to 800 nanometers. So for visible, 185 to 400 nanometers. So for visible light, we should have what's it called? We have the sample that during visible spectroscopy, the sample that should be made up of glass and not quartz, because quartz can absorb visible light. Glass will not absorb visible light. So it's made up of glass. The sample that is made up of glass. And there is a law I would quickly like to let us know for this absorbance and transmitter, because there's a mechanism here. Now this is the light coming in. Let's say the light coming, let's say UV light or ultraviolet light comes in. Once the light gets to the what's it called? Once the light gets to the cuvee, remember the cuvee must be made up with a material that cannot absorb the light. For UV spectroscopy, we use quartz. For visible spectroscopy, we use glass. For IR spectroscopy, we use rock salt as this cuvee, because these materials cannot absorb this light. So once the light gets to the cuvee, it is the material we are about to detect, the matter we are about to detect or to analyze that can absorb the light. So when it absorbs the light, it absorbs some, and some other part of the light will be transmitted. Not all the light is absorbed, some will be transmitted. So there's a law called the Beer's law, and the Lambert's law, which is together called the Lambert's law, which says that the absorbance of light, remember the light is absorbed by the sample, the absorbance of light is directly proportional or equal to the absorptivity. This absorptivity, that's A. Let me just put it here. So small a or E is absorptivity, is a constant. Absorptivity constant. Then the B is the length of the cuvee, the path length of the cuvee. Then C is the concentration of the matter. So according to Beer's law, absorbance in meters is equal to absorptivity times path length times concentration, or absorbance is equals to minus log 1 over transmittance. What is transmittance? Transmittance is the amount of light that will not be absorbed by the sample, hence transmitted to the detector. So it is the transmitted light that is read by the detector, and it is used to analyze the presence of the organic compound. Now, after a spectroscopy technique has been carried out, you usually have a detector. Now, the detector usually produces spectrum. So every spectrum has its own unique difference. For IRO spectrum, the spectrum is usually between something like this for an IRO spectrum, and we see the presence of functional group, we see their relative peaks, see their abundance, their relative peaks. We see the presence of functional group, we see their relative peaks, see their abundance, their relative peaks. So each unique peak is in centimeters. So here is the centimeters. So here is the centimeters, or in nanometer, as the case may be. Then here is what's called absorbers. So you see it is absorbed at so centimeter or at so per centimeter, depending on the graph. So we'll see, let's say this place can be 2083 per centimeter, which can be unique for a double bond or unique to a triple bond, like that. So in subsequent videos, we'll look at how to analyze the spectrum of a IRO and a UV-Vis. Remember, UV-Vis is used to detect the presence of double bonds. So for those of us doing characterizations of palm oil and vitamin A, you see in vitamin A there's a compound called retinol. Retinol is a compound very similar to vitamin A. It has a lot of conjugated double bond. So to analyze that compound, I can employ a UV-Vis spectroscopy to analyze the amount of it present in the palm oil sample. I can use a UV-Vis spectroscopy. While IRO spectroscopy is used to determine the presence of double bonds. The most popular type of IRO spectroscopy is the Fourier transform infrared spectroscopy, which uses a very high frequency of IRO length to determine, very accurate. The Fourier transform spectroscopy is a spectroscopy that is very, very sensitive. I can use a small analyte, a small concentration of the analyte to determine the presence of the elemental composition of the compound or determine the presence of the matter present. And quickly, before I end the video on this aspect of spectroscopy, now let me just drop this. Now for UV spectroscopy and visible spectroscopy, the sample should be in solution form. So if I have to analyze a compound using UV spectroscopy, the sample must be in solution. Yes, it should be in solution. But for IRO spectroscopy or FTR, Fourier transform infrared spectroscopy, the sample can be solid, liquid, or gas. But for UV-Vis, it should be in solution form. With that, we've come to the end of this lesson. And in the next video, which is spectroscopy 2, we'll look at the IRO spectroscopy and NMR spectroscopy to be very precise. And the third video on spectroscopy, I'll look at mass spectroscopy. And I told you mass spectroscopy, don't forget, it's not a true form of spectroscopy because it does not involve light radiation. I use high energy electrons, so without to be